top dead center, TDC. Premature detonation is not a problem and compression ratios are much higher. PV diagram for the ideal diesel cycle, which follows the numbers 1-4 in clockwise direction. The horizontal axis is the cylinder volume. In the diesel cycle, the combustion occurs at almost constant pressure. On this diagram, the work that is generated for each cycle corresponds to the area within the loop. The pressure volume diagram, PV diagram, is a simplified and idealized representation of the events involved in a diesel engine cycle, arranged to illustrate the similarity with a Carnot cycle. Starting at 1. The piston is at bottom dead center and both valves are closed at the start of the compression stroke. The cylinder contains air at atmospheric pressure. Between 1 and 2, the air is compressed adiabatically, that is without heat transfer to or from the environment by the rising piston. This is only approximately true since there will be some heat exchange with the cylinder walls. During this compression, the volume is reduced, the pressure and temperature both rise. At or slightly before 2 TDC, fuel is injected and burns in the compressed hot air. Chemical energy is released and this constitutes an injection of thermal energy, heat, into the compressed gas. Combustion and heating occur between 2 and 3. In this interval, the pressure remains constant since the piston descends, and the volume increases. The temperature rises as a consequence of the energy of combustion. At 3, fuel injection and combustion are complete, and the cylinder contains gas at a higher temperature than at 2. Between 3 and 4, this hot gas expands, again approximately adiabatically. Work is done on the system to which engine is connected. During this expansion phase, the volume of gas rises, and its temperature and pressure both fall. At 4, the exhaust valve opens, and the pressure falls abruptly to atmospheric, approximately. This is unresisted expansion and no useful work is done by it. Ideally, the adiabatic expansion should continue, extending the line 3-4 to the right until the pressure falls to that of the surrounding air. But the loss of efficiency caused by this unresisted expansion is justified by the practical difficulties involved in recovering it. The engine would have to be much larger. After the opening of the exhaust valve, the exhaust stroke follows, but this, and the following induction stroke, are not shown on the diagram. If shown, they would be represented by a low-pressure loop at the bottom of the diagram. At 1, it is assumed that the exhaust and induction strokes have been completed, and the cylinder is again filled with air. The piston-cylinder system absorbs energy between 1 and 2. This is the work needed to compress the air in the cylinder, and is provided by mechanical kinetic energy stored in the flywheel of the engine. Work output is done by the piston-cylinder combination between 2 and 4. The difference between these 2 increments of work is the indicated work output per cycle, and is represented by the area enclosed by the V-loop. The adiabatic expansion is in a higher pressure range than that of the compression because the gas in the cylinder is hotter during expansion than during compression. It is for this reason that the loop has a finite area, and the net output of work during a cycle is positive. 143. Efficiency. The fuel efficiency of diesel engines is better than most other types of combustion engines. 144, 145. Due to the high compression ratio, high air fuel equivalence ratio, lambda, 146, and the lack of intake air restrictions, i.e. throttle valves. Theoretically, the highest possible efficiency for a diesel engine is 75%. 147. However, in practice the efficiency is much lower, with efficiencies of up to 43% for passenger car engines, 148, up to 45% for large truck and bus engines, and up to 55% for large two-stroke marine engines. 149. The average efficiency over a motor vehicle driving cycle is lower than the diesel engine's peak efficiency. For example, a 37% average efficiency for an engine with a peak efficiency of 44%. 150, that is. Because the fuel efficiency of a diesel engine drops at lower loads, however, it does not drop quite as fast as the Otto, spark ignition, engines. 151, emissions. Diesel engines are combustion engines and, therefore, emit combustion products in their exhaust gas. Duetto incomplete combustion. 152. Diesel engine exhaust gases include carbon monoxide, hydrocarbons, particulate matter, and nitrogen oxides pollutants. About 90% of the pollutants can be removed from the exhaust gas using exhaust gas treatment technology. 153, 154, road vehicle diesel engines have no sulfur dioxide emissions. Because motor vehicle diesel fuel has been sulfur-free since 2003. 155. Helmut argues that particulate matter emitted from motor vehicles has negative impacts on human health. 156. The particulate matter in diesel exhaust emissions is sometimes classified as a carcinogen or probable carcinogen and is known to increase the risk of heart and respiratory diseases. 157. Electrical system. In principle, a diesel engine does not require any sort of electrical system. However, most modern diesel engines are equipped with an electrical fuel pump and an electronic engine control unit. However, there is no high-voltage electrical ignition system present in a diesel engine. This eliminates a source of radio frequency emissions, which can interfere with navigation and communication equipment, which is why only diesel-powered vehicles are allowed in some parts of the American National Radio Quiet Zone. 158. Torque control. To control the torque output at any given time, i.e. when the driver of a car adjusts the accelerator pedal, a governor adjusts the amount of fuel injected into the engine. Mechanical governors have been used in the past, however electronic governors are more common on modern engines. Mechanical governors are usually driven by the engine's accessory belt or a gear drive system. 159, 160, and use a combination of springs and weights to control fuel delivery relative to both load and speed. 159. Electronically governed engines use an electronic control unit, ECU, or electronic control module, ECM, to control the fuel delivery. The ECM/ECU uses various sensors, such as engine speed signal, intake manifold pressure and fuel temperature, to determine the amount of fuel injected into the engine. Due to the amount of air being constant, for a given RPM, while the amount of fuel varies, very high, lean, air-fuel ratios are used in situations where minimal torque output is required. This differs from a petrol engine, where a throttle is used to also reduce the amount of intake air as part of regulating the engine's torque output. Controlling the timing of the start of injection of fuel into the cylinder is similar to controlling the ignition timing in a petrol engine. It is therefore a key factor in controlling the power output, fuel consumption and exhaust emissions. Classification. There are several different ways of categorizing diesel engines, as outlined in the following sections. RPM operating range. Gunter-Mal categorizes diesel engines by their rotational speeds into three groups: SAD Smiley 161, high-speed engines, and GT 1000 RPM. Medium-speed engines, 300 1000 RPM, and slow-speed engines, and LT 300 RPM. High-speed diesel engine high-speed engines are used to power trucks, lorries, buses, tractors, cars, yachts, compressors, pumps and small electrical generators. 162. As of 2018, most high-speed engines have direct injection. Many modern engines, particularly in on-highway applications, have common rail direct injection. 163. On bigger ships, high-speed diesel engines are often used for powering electric generators. 164. The highest power output of high-speed diesel engines is approximately 5 MW. 165. Medium-speed diesel engines. Medium-speed engines are used in large electrical generators, railway diesel locomotives, ship propulsion and mechanical drive applications such as large compressors or pumps. Medium-speed diesel engines operate on either diesel fuel or heavy fuel oil by direct injection in the same manner as low-speed engines. Usually, they are four-stroke engines with trunk pistons winking. SAD Smiley 166, a notable exception being the EMD 567, 645 and 710 engines, which are all two-stroke. 167. Stationary 12-cylinder turbo diesel engine coupled to a generator set for auxiliary power. The power output of medium-speed diesel engines can be as high as 21,870 kW, 168, with the effective efficiency being around 47 to 48%, 1982. 169. Most larger medium-speed engines are started with compressed air direct on pistons, using an air distributor, as opposed to a pneumatic starting motor acting on the flywheel, which tends to be used for smaller engines. 170. Medium-speed engines intended for marine applications are usually used to power ro-ro ferries, passenger ships or small freight ships. Using medium-speed engines reduces the cost of smaller ships and increases their transport capacity. In addition to that, a single ship can use two smaller engines instead of one big engine, which increases the ship's safety. 166. Low-speed diesel engines. The MAN B and W5S50MC, a two-stroke, low-speed, inline 5-cylinder marine diesel engine on board a 29,000-ton chemical carrier. Low-speed diesel engines are usually very large in size and mostly used to power ships. There are two different types of low-speed engines that are commonly used: two-stroke engines with a crosshead, and four-stroke engines with a regular trunk piston. Two-stroke engines have a limited rotational frequency and their charge exchange is more difficult, which means that they are usually bigger than four-stroke engines and used to directly power a ship's propeller. Four-stroke engines on ships are usually used to power an electric generator. An electric motor powers the propeller. 161. Both types are usually very undersquare, meaning the bore is smaller than four-stroke. 171. Low-speed diesel engines, as used in ships and other applications where overall engine weight is relatively unimportant, often have an effective efficiency of up to 55%. 1. Like medium-speed engines, low-speed engines are started with compressed air, and they use heavy oil as their primary fuel. 170. Combustion cycle. Four-stroke engines use the combustion cycle described earlier. Two-stroke engines use a combustion cycle which is completed in two strokes instead of four strokes. Filling the cylinder with air and compressing it takes place in one stroke, and the power and exhaust strokes are combined. The compression in a two-stroke diesel engine is similar to the compression that takes place in a four-stroke diesel engine. As the piston passes through bottom center and starts upward, compression commences, culminating in fuel injection and ignition. Instead of a full set of valves, two-stroke diesel engines have simple intake ports and exhaust ports, or exhaust valves. When the piston approaches bottom dead center, both the intake and the exhaust ports are open, which means that there is atmospheric pressure inside the cylinder. Therefore, some sort of pump is required to blow the air into the cylinder and the combustion gases into the exhaust. This process is called scavenging. The pressure required is approximately 10 to 30 kPa. 172. Schematic of a two-stroke diesel engine with a Roots blower Detroit diesel timing due to the lack of discrete exhaust and intake strokes. All two-stroke diesel engines use a scavenge blower or some form of compressor to charge the cylinders with air and assist in scavenging. 172. Roots type superchargers were used for ship engines until the mid-1950s. However, since 1955 they have been widely replaced by turbochargers. 173. Usually, a two-stroke ship diesel engine has a single-stage turbocharger with a turbine that has an axial inflow and a radial outflow. 174. Scavenging in two-stroke engines. In general, there are three types of scavenging possible: uniflow scavenging, cross-flow scavenging, reverse flow scavenging. Cross-flow scavenging is incomplete and limits the stroke, yet some manufacturers used it. 175. Reverse flow scavenging is a very simple way of scavenging, and it was popular amongst manufacturers until the early 1980s. Uniflow scavenging is more complicated to make but allows the highest fuel efficiency. Since the early 1980s, manufacturers such as MAN and Sulzer have switched to this system. 126. It is standard for modern marine two-stroke diesel engines. 2. Fuel used. So-called dual-fuel diesel engines or gas diesel engines burn two different types of fuel simultaneously, for instance, a gaseous fuel and diesel engine fuel. The diesel engine fuel auto-ignites due to compression ignition, and then ignites the gaseous fuel. Such engines do not require any type of spark ignition and operate similar to regular diesel engines. 176. 177. Fuel injection. The fuel is injected at high pressure into either the combustion chamber, the swirl chamber or the pre-chamber. 142. Unlike older petrol engines where the fuel is added in the inlet manifold or carburetor, engines where the fuel is injected into the main combustion chamber are called direct injection (DI) engines, while those which use a swirl chamber or pre-chamber are called indirect injection (IDI) engines. 178. Direct injection. Most direct injection diesel engines have a combustion cup in the top of the piston where the fuel is sprayed. Many different methods of injection can be used. Usually, an engine with helix-controlled mechanic direct injection has either an inline or a distributor injection pump. 159. For each engine cylinder, the corresponding plunger in the fuel pump measures out the correct amount of fuel and determines the different types of piston bowl stemming of each injection. These engines use injectors that are very precise spring-loaded valves that open and close at a specific fuel pressure. Separate high-pressure fuel lines connect the fuel pump with each cylinder. Fuel volume for each single combustion is controlled by a slanted groove in the plunger which rotates only a few degrees, releasing the pressure, and is controlled by a mechanical governor, consisting of weights rotating at engine speed constrained by springs and a lever. The injectors are held open with fuel pressure. On high-speed engines, the plunger pumps are together in one unit. 179. The length of fuel lines from the pump to each injector is normally the same for each cylinder in order to obtain the same pressure delay. Direct injected diesel engines usually use orifice-type fuel injectors. 180. Electronic control of the fuel injection transformed the direct injection engine by allowing much greater control over the combustion. 181. Common rail, CR. Direct injection systems do not have the fuel metering, pressure raising and delivery functions in a single unit, as in the case of a Bosch distributor type pump. For example, a high-pressure pump supplies the CR. The requirements of each cylinder injector are supplied from this common high-pressure reservoir of fuel. An electronic diesel control, EDC, controls both rail pressure and injections depending on engine operating conditions. The injectors